Hi guys, today's lesson is 2.5 on different types of energy. So energy, when we define it in science, is first of all of scalar quantity. So energy doesn't have a direction. And it's in physics the ability to do work. And work is whenever you apply a force and an object moves a distance. So anything that can move due to a force is going to have energy. So lots of different types here. We have potential energy, kinetic energy, thermal energy, nuclear, elastic, and many, many different types. This lesson is going to focus on gravitational potential and kinetic energy. So, one big thing that we need to study in physics is something called the law of conservation of energy. Now, in chemistry, we looked at the law of conservation of mass, being there's not going to be mass that's created or destroyed. Mass can just change forms. So, in a chemical reaction, it might change from an aqueous solution to a gas, for example. But if you're able to measure the entire mass, it always stays the same. Similar idea here with energy is energy cannot be created or destroyed out of thin air. It can only change forms. So where something might start as nuclear energy, let's say, when it's transformed, it might become thermal energy. So energy is always transforming between these different types. So this is very important in physics. The law of conservation of energy, it can't be created or destroyed. It changes from one form to another, but the total amount never changes. And one kind of interesting tidbit is that all of the energy in our solar system comes from one place. Every piece of energy that we have is from our sun. Now, this is what we're focusing on in Science 10, so potential energy and kinetic energy. And I should clarify here, we're focusing on gravitational potential because there are different types of potential energy. If you have a rubber band and you pull it back, that's got potential energy because if you let go, we all know what happens. Chemical potential energy, if I have some vinegar sitting next to some baking soda, that has the potential to release a lot of energy, but I need to mix them together before I get that energy. So what we're talking about is potential energy in terms of gravity. So I always think of potential energy as the ability to fall down and go boom and hurt yourself. So if you're standing on, let's say, a chair, you have the potential to be acted upon by gravity and fall to the floor and go boom. Okay, that's what gravitational potential energy is. So anything that has a certain height above, say, the ground is going to have gravitational potential energy because we know that we can't get away from gravity. It's always acting on us. And if we're above the ground, we have the potential to fall and hit the ground. Now, kinetic energy is energy in something that's moving. So in Science 10, we talk about dropping objects. So maybe I'm going to drop a skydiver out of a plane, and they're going to have potential energy to start with, and then it's going to change to kinetic because they end up moving faster and faster and faster. The faster they go, the more kinetic energy they have. We can have other types of kinetic energy in other courses as well. Like in Physics 30, we study the kinetic energy of light or photons. And heat and electricity are also moving objects that produce kinetic energy. So here's the first formula, gravitational potential energy. We call it EP for energy potential, is equal to mass times gravity times height. So it's a pretty simple formula. You're just timesing everything. So this is going to be stored energy that an object has in reference to its height. So if you think about going to the swimming pool, would you have more stored potential energy if you were on the 1 meter diving board or the 5 meter diving board? Pretty obvious. We'd have more energy the higher up we are. Okay, so height has a big thing to do with that. And gravity here, this is something that we use as an average for our planet Earth. So 9.81 meters per second squared. This is the acceleration due to gravity on Earth on average. So it actually can change. If I go to the top of Mount Everest, there's going to be less acceleration due to gravity because I'm further away from the sea level, the regular surface of Earth on average. If I go way down to the bottom of some trench somewhere, I might have more gravity because I'm closer to the center of the planet. So to make things simple in Science 10, we just use the average acceleration due to gravity on Earth as 9.81. This is a constant. It's found in your data booklet and on your formula sheet, although we'll use it so much that you'll memorize it. So since it's a constant, it's not going to count towards your sig digs. Remember, every answer you have in physics is written to the right number of sig digs. 9.81 will never be a number that you use to figure out sig digs. Okay, first example, it actually has nothing to do with potential energy, but a concept that we get wrong in daily language. So in English, we say this wrong. And in science, it means something different. So Brad has a mass of 65 kilograms. What is his weight? So actually, we say this in everyday language wrong because we would say that's his weight, right? When you go to get your driver's license and they ask you what your weight is, you tell them your answer in pounds and then they usually change it to kilograms. You haven't actually told them your weight, you've told them your mass. So your mass is measured in kilograms. It's how much matter makes up the object. Is your mass going to change if you go to the moon? How much matter you're made up of, that's not going to change if you go to the moon. You're still the same amount of matter. What's going to change, however, is your weight. So when we say we want to lose weight in everyday language, what we actually mean is we want to lose mass. We don't want to be made up of as much matter. To lose weight, there's really only one way that you can do that. You need to go somewhere with a lower acceleration due to gravity. So if I went to the moon right now, I actually would lose weight because acceleration due to gravity on the moon, I think, is 6 point something. It's way less than it is on Earth. If I wanted to lose even more weight, I could go to Mars, where the acceleration due to gravity is 3 point something. But if I'm talking in everyday language about losing weight, wanting to be thinner, I would actually mean my mass. Because what weight means in physics is weight means the force of gravity acting on you. Okay, so force of gravity is equal to your mass times acceleration due to gravity. Now, some textbooks will give this is a vector. Some textbooks will call it W for weight as a vector. But just in preparation for Physics 20, I prefer to call it FG because it is a force, and we will be studying forces in pretty good detail in Physics 20. So what would we do? We would say mass is 65 kilograms. Acceleration due to gravity is 9.81 meters per second squared, and we want to figure out what the force of gravity is, or what weight is. The formula I've already written down, and actually G over here is a vector as well, because gravity acts in a certain direction. Gravity always acts towards the center of the planet. So here I go subbing my numbers in, 65 kilograms and I'm going to correct this. This should have a negative on it for G because the negative is the direction towards the center of the Earth. So let me pop this in my calculator here, and I get negative 637.65. Now that answer would lose me some marks because of two reasons. No sig digs and no units. So let's talk sig digs. We know that the 9.81 does not contribute to sig digs, but the 65 does. It has two sig digs. So I'm going to write my answer over here with two sig digs. The only way that I can do that is with scientific notation. So I look at the beginning of the number, and I'm going to write two digits. And the second one, the 3, if it needs to be rounded, it's going to be rounded. Yes, there's a 7 after the 3, so I'm going to round it to a 4. Okay, I wrote it as a number between 1 and 10 because now I can do my scientific notation and tell it to move the decimal 2 over. That's where the decimal actually is in the 637 number. So now the number is written correctly with sig digs. We just need units. And force is actually named after a famous old dead guy. Some dead guy that got hit on the head with an apple and is famed with discovering gravity. So if you know his name, you know what this unit stands for. It stands for newtons. So there we go. Now you can explain to your family that when we talk about weight in everyday language, we're not actually talking about scientific weight. We use it in a different way. Now let's do some examples with that formula for potential energy. So we have a 7-kilogram box, 2 sig digs, sitting on a shelf 2.5 meters above the ground. What is its potential energy? Let me list my variables. Kilograms. When you see that, you should know what that stands for. That stands for mass. 2.5 meters. Meters is your height. And when we're talking about something falling, we're always going to assume that G is 9.81. We don't have to use the negative like we did in the last question because energy is a scalar. So we can just use 9.81. Here's my formula. Potential energy is mgh. Here's my substitution step. You can see I'm writing the numbers with all the sig digs that they were given in the question with. And I'm writing the units in my work. This is really important when we study physics and chemistry, but we didn't necessarily focus on it in our chemistry unit because we didn't have that many calculations. We just calculated the moles. So in physics, I'm really going to be looking for your work to show me units and sig digs the whole way through. Now, this is all just multiplying. So on my calculator, I'm going 7 times 9.81 times 2.5. And I'm going to write the number down that I get on my screen just so we can look at it and figure out how to put that into 2 sig digs. This again is scientific notation. You can see how important it is to be good at these skills that we learned in the first week. If you don't know how to do scientific notation, then actually our Science 10 final exam, you'd get the whole physics section wrong because pretty much the whole thing is scientific notation. That's just the nature of physics. The numbers that we work with are usually really big and the sig digs can be really small. So we need to know how to write these big numbers just with 2 sig digs, for example. So here I go. I'm going to try and write a number between 1 and 10 from the beginning numbers here with 2 sig digs. That number would be 1.7. I don't round because there's a 1 after the 7. Then I'm going to say I put my decimal between the 1 and the 7. How many places do I have to move it to get it where it actually is? 1, 2. Since I went to the right, it's a positive 2. If I had gone to the left, it would be a negative 2 exponent. Now, the energy units, you'll have to memorize this, another famous old dead guy, but the energy units are joules. Okay, let's try another one. A 45-kilogram diver is standing on a platform. She has 5,345 joules of potential energy. How high is the platform? I see 3 sig digs and 4, so my answer will be written with 3. I see kilograms, which stands for mass. And I see joules, and they tell me that that is potential energy. I always know G. And they're asking me how high. So what is the height? Here's my formula. And here I'm going to sub in. So on the left side, I'm going to put my potential energy. And then I've got mass times G times height, which I don't know, so I'll leave it as just an H, a variable. Now in algebra, what would we do first? I would go 45 times 9.81 right here, and I get 441.45 times H equals 5345. Now, if I wanted to isolate H and it's timesing by something, I need to do the opposite, which is divide. What you do to one side in algebra, you do to the other. They cancel on that side, and I'm going to get a height of, so on my calculator I see 12.10782648, but looking back up at my work, I see I have to write 3 sig digs. 12.1. And you're just going to have to memorize the units. They're usually pretty obvious, like height would be measured in meters, but if you're struggling with that, you're just going to have to spend time memorizing. It's not centimeters, it's not kilometers. In physics, we use meters. And that brings us to the end. So you have a practice section on lesson 2.5, potential energy. If you have any questions or you want me to look at your work and see if you're forgetting anything, just send me an email. I'd be glad to help.